It's the last talk. So it's a work that was done with my former student, Dimitri Chinadze, my former student, Yushan Wang, who is for a number of years professor in Florida, and actually for exchange student and then postdoc Laura Klassen, who is now has a number of faculty positions in Germany. And before I start talking, two disclosures. First, I'm a substitution for Alan McDonald. So I'm not supposed to give a talk at this conference. Alan did many things, and we heard in the previous talk that Alan pioneered not only the whole business with twisted bilayer graphene, but also some other things. What I will do is a small amount of the stuff that Alan did, and you will see at some corner that I will show you where there is interplay with what Alan did. And second, I consider this as basically button transfer, button exchange in the relay from one workshop to the other. So one workshop is about to end, and our workshop is about to start. Well, actually started this week, so it's this one. Okay, so I'll be talking about metals. This will be talk about metals rather than insulators. And it will be talk about itinerant scenario for spin and value ordering in bilayer graphene. And I will start with untwisted graphene, and then I will go into dangerous business of twisted graphene. So let's start. So first part is about untwisted Bernard bilayer graphene. It's graphene in which if you take upper layer and take, say, spin from B sublattice, it's on top of spin of A sublattice in the lower level. If you take spin of A sublattice, it's right in the middle of the hexagon of spins in the lower level. And this material has been studied to death a number of years ago. And it was mostly interested because of this quadratic band touching and even more sophisticated stuff. It includes trigonal warping. And there were a number of people who were doing RG and various ordered state in this situation. But new life started several years ago when people applied perpendicular electric field displacement field. And displacement field essentially splits excitations into two layers. So you essentially come back to one layer graphene when your chemical potential, say, in the conduction band or in the valence bands, is really one layer story, but with a twist. Dispersion becomes extremely flat at the bottom of the valence bands and at the top of conduction bands. You can see it here. We can play the game dispersion K4, K6, but it's just it is as it is. And this creates an interesting situation when you don't have a flat band. The bandwidth is still volt, but the top or bottom of the band is extremely flat. And so if chemical potential is very close to this position, then you open up a small Fermi surfaces. And you deal up with the situation when you have interacting fermions with small Fermi pockets. And the question is, of course, where these Fermi pockets are located. And they're located around Dirac points K and K prime. So you have a story when you have two values near K and K prime, you open up Fermi surfaces, and then the question is what you get out of this. The situation is a little bit more complex than just two circles that I put in. If you look at actual situation, you find out that this story, this consideration is either close to K or close to K prime. So you start with three small pockets centered around the K point. Then if you change electron or hole doping, at some points this corners of this Fermi surfaces merge. You have Van Hoff point, either conventional, or if the corners, actually if they all merge at one point, it's even higher order Van Hoff point. And then you end up with one single Fermi surface. It's still small. The chemical potential is still very close, say, to the top of the valence band. So we're not talking about basically filling the whole band by any means. But you see a clear evolution. And of course, somewhere in the middle, when there is a Van Hoff point, density of states is the largest, and this is the point where inverse compressibility goes to zero. And of course, every state is fourfold degenerate, 2 for spin and 2 for value. This experiment done here is experiment from Andrey Young group. you take particular value, or I took particular value of displacement field, and then you change density. And then you see you go from a state which they call symmetric state to another symmetric state. But if you look carefully, you find there is a number of black lines, and color coding here is such that black lines are inverse, basically color coding is inverse compressibility. Black lines is where inverse compressibility go to 0. If it would be free fermions, you expect just to have one black line, and then two states of free fermions. One is with small Fermi surface, another is with also small, but with one instead of three. And even more, when you look at the data, which is fast Fourier transform of resistivity, you see oscillations, and you can figure out from these oscillations, it's a magic to me, but it was figured out, how many Fermi surfaces you have, and what's the genericity of these Fermi surfaces. And if you look at this, you find that endpoints are exactly what you expect. You start with small pockets, and they're fourfold degenerate. You end up with larger pockets, which are also fourfold degenerate. But in between, you clearly lose this fourfold degeneracy. And this loss of degeneracy means that the system goes into some other state. So what I think this experiment suggests is that in the process of going from one end to the other, the system goes through the sequence of phase transitions. The question is, what are these phase transitions and what are these ordered states? And pretty similar results have been obtained for rhombohedral three-layer graphene. So let me focus on this one first. So let me do something very simple. This really last talk of the conference, so it will be less sophisticated than any other talk on this wonderful conference, so I'll do something very simple. I'll just say, suppose I take just simple circular Fermi surfaces close to k and k prime points. I have this wonderful new element, valley. I have two valleys. So I introduce two fermions, one near valley k, another near valley k prime, and ask a simple question. I want low energy states. I have red and blue Fermi surfaces, red and blue fermions. So how many bilinear combination of these fermions I can create? Density doesn't matter. Density is fixed. A dagger A plus B dagger B is not an order parameter. But I can create difference between occupations of two valleys, and this is sometimes called valley polarization. It's charge order. I can create ferromagnetism within each valley, and out of ferromagnetism within each valley, I can create either total ferromagnetism or total antiferromagnetism with either same or opposite signs of ferromagnetic ordering in the two valleys. And then I can create two orders with finite momentum between k and k prime. One is, I prefer to call it charge density wave with momentum 2k, because k minus k prime is the same as 2k, but sometimes it's called charge intervalley coherence order. And similarly, you can create spin intervalley coherence order. And this all you can do out of this two types of fermions plus spin. And then you calculate how many order parameters total you have. There are 5 different combinations, actually, sorry, 4 different combinations. But there is, of course, degeneracy because sigma can have sigma x, sigma y, and sigma z. And when you count how many different order parameters you can have with the total number, you immediately find that the total number is 15, which is, of course, the same as for number of generators of SU4. And so the word SU4 immediately comes into play, but this is itinerant SU4. So what to do next? There's a number of order parameters, but nobody said that they will develop. So what one should do is to, of course, introduce interactions. And there are generally 3 different interactions. Again, the maximum you can write. You can write either interaction within one valley or density-density interaction between valleys or exchange interaction when you go jump from one valley to the other. There's 3 possibilities. And with 3 interaction plus 2 different polarization operators, either at 0 momentum transfer or with momentum transfer k minus k prime, you can write down conditions for all these order parameters. And in fact, this is where interplay with Alan MacDonald is, because I guess he was the first to say that this exchange interaction is extremely important for the developments of either ferromagnetism or antiferromagnetism. And this way, it becomes basically zoo story that I can play with polarization operators, I can play with interactions, and I can find actually any order that you want be the leading order. What I want to do is to constrain theory a little bit more and say that what if we only consider interaction with small momentum transfer, because the one with larger momentum transfer is of course screened and we expect it to be smaller. And if I do this, and I take polarization operators to be the same, which is expected because there's almost complete equivalence, at least to second order in deviation from k and k primes, the polarization operators are the same, then you find out that there is a single condition for all 15 order parameters. It's just Stoner-like condition, which looks very simple. There is one non-triviality here, is that some of the orders are charge orders. And normally for repulsive interaction, you don't expect charge orders to develop, but here, of course, there's a special charge order. For example, value polarization is A dagger A minus B dagger B. And so, in fact, this order developed pretty much by the same reasons as we get, say, S plus minus superconductivity in pnictides. But anyway, this is very similar to what Leonid Glazman was talking at this workshop, I guess, 2 weeks ago, that despite that some orders are charge orders, they have Stoner-like instability. So long story short, there is one condition for all the 15 order parameters, interaction time polarization operators, and then we have a standard Stoner story. If we allow interaction to be such that u pi larger than 1, we get instability. The question is what kind of instability we get. On a first glance, you have complete symmetry between 15 order parameters, and of course, any quadratic Landau function will just have a square of these 15 order parameters, but it doesn't mean that any combination of the 15 will eventually develop, because it all depends on the form of Landau functional for symmetric order parameter by taking it first and fourth order in the interaction, in the order parameter expansion, And for this, it's magnetic conference. So it's convenient to write this all order parameters as magnetic by introducing isospin instead of Valley variables. Then all these order parameters are just different combinations of spin and isospin orders. It's the same order parameters. And then I can write, or I can derive by Haber-Stratonovich, in fact, we derived it, Landau functional, and its expansion in terms of trace of this 4x4 matrix. And in fact, Arkady Weinstein is here. There was a lot of discussions with Arkady about the structure of this free energy. Number of people studied SU4 model before, but this is something special case because it's really itinerant SU4 model. And in particular, all coefficients are expressed in terms of loop diagrams for fermions. And if you write down all these traces, they can also be expressed in terms of the 15 bilinear combination of fermions, this 15 order parameters. And of course, it's symmetric with respect to SU4 by being trace. One can work with this. It looks a little bit ugly, but still workable. And in fact, first time we did all calculations for just this functional. Before we realized it's something more simple, that it's traceless 4x4 matrix. So you can, if you want to calculate trace of phi square, phi cube, etc., you can just put it in a diagonal form, and this gives you just 3 constants: lambda 1, lambda 2, lambda 3. And then you have a Landau functional as a function of 3 variables. This is doable. And outcome of this, there are 3 solutions, only 3. I mean that not any combination. And I will tell you in a second what the solution means in physical sense. But each solution, just let's not go into all details. For each state, broken symmetry is a closed space. Each solution has a pretty large number of Goldstone modes. And you see these 2 solutions look like fundamental solutions, and this is something intermediate. And this is exactly what happens. In terms of real variables, spins and isospins, either value order or spin order, one solution is actually a mixture of spin and value orders, a necessary mixture, with particular ratio of the 2 orders, such that, for example, you can have value polarization. This is supposed red and blue not equal is supposed to mimic valley polarization or decayed valley polarization, and we have ferromagnetism, but only in one valley. There is no magnetism in the other valley. It's just one example of the states. And what will be important for me is how each of states affect fermions, because this was measured. And so each state from this degenerate set, there are 6 gallstones in this state, but each state from this set splits fermions in 3-to-1 or 1-3 fashion. Namely, 4-fold degenerate levels split such that there are 3-fold degenerate and a singly degenerate level. Another state is with the letter OR. It's either valley or spin order, but not a mixture. And with 2 examples, that is either pure valley polarization, blue and red are of different height, or pure magnetic order, ferromagnetism in one valley, ferromagnetism in the other valley, and arbitrary angle between ferromagnetic order in these 2 valleys. Splitting is 2 by 2. It's clear here, you just split 2 valleys, but don't do anything with spin. And there is a third state, which is intermediate state between the 2. It splits into 2-1-1 fashion or 1-1-2 fashion, but basically 2-1-1. Very good. So what I will need to do? I will need to do basically childish work. I have 3 solutions. I have free energy. So calculate free energy or Landau and functional, in fact. For these 3 solutions, see which one develop. And for this, basically, I'll do the following. I assume, and this is really assumption, that quadratic coefficient, which knows about whether any order develops, is of course with some coefficient 1 minus u pi, and I assume that 1/2 actually there is a way to increase.
Something very simple. So for most of the orders, suppose we don't think about SU4, for most of the orders, there should be some discrete symmetry which forbids the cubic term. Actually, you're saying that cubic term.
Cubic term is allowed here. It's trace of phi cube. This term is allowed. Coefficient may be 0. Coefficient may be 0. We'll talk about this. That coefficient may be 0. So generally, if you expand to linear order, generally near the Fermi surface, cubic coefficient, of course, 0. You need to go beyond. But here, when we have 1/2, story is different. You expand to quadratic order with the dispersion, and this coefficient is non-zero. Except for right into that 1/2 point when it's 0.
Yeah, I know in general the cubic term should be there. I'm just saying, so if you look at, for example, like the male order, it's part of SU4, right? But then that's SU2. I know. But it's part of the SU4.
Yeah. When n is larger than 2, it's lower. Yeah. No, it's okay. Yeah. Can we? Yeah. Okay. So here is the simplest part of the story. So I assume that there is a range of doping where the system develops order. So we'll discuss which one, but the order is there means that this coefficient becomes negative. And then it turns out you calculate 3 energies for these 3 states, and it turns out that they actually depend on a single parameter. And this parameter is the ratio of this coefficient. There is another parameter, the ratio of 2 coefficients that you can write at 4th order, but it means nothing. It's really, nothing depends on the second coefficient. And it was a good question, because if I consider free fermions, and I'm right at 1/2 point, then and expand to quadratic order, gamma is 0. But if I shift a little bit, then gamma changes. Gamma is basically d to n over d mu squared. It's a product of 3 green functions. And therefore, this guy changes sign between being on one side, smaller doping, and being on the side of 1/2 on the other, on the larger doping. So basically, in terms of this variable x, I go from large positive x. If I always hear that take this alpha negative. So I go for large positive x to x equal to 0 to large negative x. I need to calculate these 3 energies and see what's going on. And long story short, again, it turns out that this intermediate state, which is shown here as red, is always quite close, but it's never winner. So you have 2 clean states, either one of them or another one. So read it like this: either valley and spin order, or either valley or spin order. Of course, if I relax the restriction of exact SU4 symmetry, intermediate state may happen, but then I go into fantasies. When I say 1A and 1B is just the same state with spin n value order, but just for two different values of gamma, and it means splitting is either 3-1 or 1-3. And basically then this is what comes out. This is in fact our result. The rest will be just applying this result to look at experiment. We have spin and value order first when long range order develops. And this is the state which splits fermions in 3-1 fashion. Then we have another state and first order transition between this one. The state which splits fermions into 2-2 fashion, and order is either value or spin, or maybe something more complex when I introduce finite momentum transfer. Again, every order is a combination of these 15 variables with X number of gallstones. And then again, I go back into order number 1, but splitting is now into 1-3 fashion. So it's just this. And then we lose long range order. And now I go into really dangerous business. Because now you start applying this to, first of all, Bernard bilayer graphene. There are a number of states, and we label the states in the same way in experiment. And long story short, that some of the states are pretty much the same as in experiments. Some I don't quite understand, because I would understand, for example, this state as basically one large Fermi surface and 3 small Fermi surfaces. Only one is seen here, and I don't exactly know why it's like this, but it's similar anyway. What I'm just saying is very simple stuff, that we see a sequence of ordered state. When the system goes in change doping, you start with a state which is disordered, you end up with a state which is also disordered. This is a state far away from Van Hoff point. Somewhere in between, the system crosses through Van Hoff region, and point is that when it starts to approach Van Hoff, instead of being at Van Hoff, the system develops long range order. And then it keeps going, and it develops another one, the third one, and then finally order disappears. But there is a sequence. And at this point, I go to a really dangerous business of asking whether anything like this can be seen in a system which is traditionally considered as a strong coupling system, and strong coupling approaches are majority for this field. This is twisted bilayer graphene. But my point will be based on two observations. Both come from STM data from Ali Yazdani group. Similar data from other people. I just don't want to bother representing too many data. If you look at what happens close to charge neutrality before you dope by either holes or electrons, and you have two peaks. It's a question, of course, how you interpret these two peaks. But if you interpret these two peaks as continuity from different angle as Van Hoff points, then the distance between these two Van Hoff peaks is about 35-40 MeV. There is definitely some effect of interaction, increased width between the peaks. But you can go to either larger electron doping or larger hole doping when both peaks are on one side of the chemical potential, then the width is smaller, but it's still 15-20 MeV. And generally, it means to me that the width is roughly comparable to 1/100th of electron volt. So it's the same as interaction strength, although nobody can probably say more than this. This is number one. Number two is something that Paco Guinier, in fact, emphasized in one of his papers first, that over range of dopings, when you look at where is this Van Hoff peak, it's supposed for free fermions, it's supposed to come to the Fermi surface, cross it, and then move. In fact, it's almost confined to the Fermi surface all the time. It doesn't move far away from it. And with this, I want to play a little bit with Van Hoff physics when looking at this material. And in practice, it means that what I'm doing, I'm borrowing the result from Liang. It's his dispersion. So let's take the dispersion. Details doesn't matter, because whatever dispersion you write down, there must be Van Hoff point, because you start with small pockets around K and K prime. You ended up with some large Fermi surface around gamma point. So Van Hoff must be there. But there is a big difference with previous case. Now I have situation when there is a 3 Van Hoff point of one color, let's call them again valley, and 3 Van Hoff points are another color. So altogether we have 6 Van Hoff points. There's even situation when there are 12 Van Hoff points. So it's a bizarre story. And if I quickly look into this 6-patch model, meaning that I want to look at formulas near Van Hoff points, then first of all, I have 3 different momenta connecting Van Hoff points. I have 3 different possibilities to connect these Van Hoff points, and total number of order parameters is an unimaginable 143. In fact, somebody can realize that 143 is the number of order parameters for SU12. But in reality, then what we did, we used Canvafic interaction, which is basically a combination of Hubbard and exchange from sublattice B to sublattice A in real space. So it's basically either pair hopping or exchange interaction within a given hexagon. And with this, you calculate the zoo of susceptibilities for different order parameters. 143 is, of course, just to impress, because, of course, some of them are degenerate because of spin, etc. But nevertheless, when you do it and you plot everything as a function of this, in fact, parameters that tells you how strong is interaction between A and B sublattice, then you take magnifying glass and you find that, in fact, there are only 2 susceptibilities that really go up. So the system basically shows tendency towards 2 types of orders. And when you look closely, what are these orders, you find that you can call them the same way. One order is Valley polarization, another is a Q equal to 0 orders. Another order is ferromagnetism within Valley, and then there are 2 orders with a finite momentum, and this, in fact, S-wave component of this order with momentum between neighboring Van Hoff points. This is the same 15 orders. Same generators, or they form a joint representation of SU4. And then, therefore, you have the same ordered state. One is, again, Valley and spin, another is either Valley or spin, which means the same line of transformations under Hall or under electron doping. The difference is now it's real doping. I go from n equal to 0 to n equal to +4 or n equal to -4. And my Van Hoff points, actually, they start on both sides of chemical potential, 2 of them. They end up both on either on the left or on the right of chemical potential. But here's a few minutes, so I'll try to be quick. I want to quickly describe how one can go from a situation with charge neutrality, when you have 1 Van Hoff point above and 1 Van Hoff point below chemical potential, to the, say, what happens under electron doping, when you have both of them below chemical potential. For free electrons, they just move. For this scenario, what happens is that, again, one of Van Hoff points approaches chemical potential, but this is where order develops. It splits. It first splits into 1-3 fashion, then another order develops, and basically one component of this guy moves, and you have 2 and 2, then 3 and 1, and then finally the 4 components are reconfined here, and you get 4 time degenerate Van Hoff peak. You judge for yourself. These are actual data from Ali Yazdani group, which we got. And in any way, whatever this picture is, you clearly see, for example, here, then when peaks moves through Van Hoff peak moves through chemical potential, it splits into several subpeaks. I think it's pretty clear here that there is a splitting into several subpeaks. And then, of course, here is what we want to say, that I clearly see 1-3 splitting to 2 and 3-1, and there's probably 1-1-2 splitting here as well. So it looks that it's similar to what we are seeing. And final thought, I'm almost done. In this set of data, I mentioned that color coding is inverse compressibility, and there's the lines where inverse compressibility is 0, means compressibility tends to infinity. And the same was seen by Riccolo-Lani group in Weizmann. I guess Yuval Arek is a collaborator on that paper. And it's again set of seesaw behavior of dmu over dn, which obviously indicates a number of phase transitions. And quite a number of groups looked at this, but their explanation in one way or another was that one of the bands get completely filled and then goes out of the picture. Our explanation is not that different, but there is qualitative difference. What we are saying is that once, say, fourfold degenerate peak, 1/2 peak comes to the Fermi level, d mu over dn goes to 0. At 1/2 point, dn over d mu diverges. But before it goes to 0, order develops, and then all components of the peaks move away from the Fermi level. Once they move away from the Fermi level, d mu over dn jumps to a finite value. So you get this, and then the process repeats itself when the remaining 3 components again approach Fermi level, again split, then 2 remaining components approach Fermi level, split, and finally last component just goes through. That's basically what I wanted to say. So conclusions of what I just told you is that we see that close to 1/2 singularity, there is in both cases untwisted and twisted graphene. At least if we consider untwisted graphene in a itinerant region, then we see dominant 15 order parameters, which form adjoint representations of SU4. And when we look what kind of order can develop, we find only 2 types of order. One type of order is when you develop simultaneously valley and spin order with particular ratio between the two, such that splitting of electron levels is 3:1 or 1:3. And another state when we have spin or isospin order, either or, say valley polarization or ferromagnetism in both layers, and this one that splits levels into 2-2 fashion. And again, each state has quite a number of gallstones. And when we change doping, either way, either hole or electron, we go from state 1 then to state 2 and then to state 1 back. So it's cascade of phase transition in this regard. And the very last slide. Of course, when we apply this to BBG, Bernard bilayer graphene, we're more or less on safe ground. The systems are metals. And there are no experiments that will show real topological properties of this. When we apply the results to twisted bilayer graphene, of course, we cannot come to a most interesting regions of integer fillings, and this is a metal. We start with the metal. So all we can say is that how system develops order, and then order can bring the system into an insulating state. And our main argument, of course, similarity between experiments on cascade of phase transitions. But I want to finish with one just remark here, that with all metallic systems, we deal with Lattinger theorem. So the question is when Lattinger theorem allows insulating state. And we know this from simple example of antiferromagnetic order. Antiferromagnetic order that splits Fermi surface into hole pockets, electron pockets, and there's a Lattinger theorem for antiferromagnetic order, that the difference of the areas between these two pockets, in fact, doping X. So at half filling, the difference is 0, and this is why you increase interaction, both Fermi surfaces, hole and electron disappear simultaneously, we go into insulator. So I guess this argument basically tells you that if you start with a metal and introduce an order for a metal, then Lattinger theorem tells you that yes, it's integer fillings, you can have insulator, and if its filling is not integer, then some form of metallicity most likely survives. That's it. Thanks.
Thank you, Andrey. So, questions? Let me start. Oh, okay.
Let's not ask anything since nobody else is bothering Lipo. So the question in the first part, I have no problem with your symmetry analysis, but I'm missing something. One can just directly do a full Hartree-Fock theory, incorporating all the symmetry, incorporating the D field, incorporating the band structure, and I know because we did it, and get more or less quantitative agreement with the experiment, with the color and so on also. So what are we gaining by your analysis?
I guess the point that I repeated several times is that we know what kind of order develops. And I was amazed that there are 2 types of order. I thought it would be many different ones.
No, but Hartree-Fock incorporates that because you incorporate symmetry. I mean, we don't talk about these things in the paper because it's kind of obvious, but you know, symmetry is exactly what you said.
Right. If somebody says that you don't need to do this, you do all this without even looking into SU4 free energy.
No, you cannot do that. That's too big.
Yeah, you need to. So in some sense, if somebody comes and said, I did before what you guys did, and I find these two orders, I can only say, well,
no, but
sorry.
For example, in your case, you do not do anything with the D field, right? D field doesn't come in anywhere in your...
D field just flattens the dispersion.
Correct. But to get quantitative agreement, the D field is crucial because it's changing the band structure, changing the thing. And connected with that, you don't have an intervalley coherence phase anywhere. I mean, that should be there, right? You're not getting this at all.
Very good question.
Yeah, I mean,
the reason
I missed something. Yeah.
No, you didn't miss something. It's me. The phases, both states, which I showed, can be written in terms of of this order. I just use Q because it's easier to explain.
Yeah. We have no disagreement.
Thanks, Andrey. Yeah, I mean, I like it because it's simple. But let me ask from sort of a, let's say, more theoretical point of view. You're using the assumption that from the experiments you think it's Q equals 0 order. But from if one doesn't know that and knowing, is there a good reason to have Q equals 0 order theoretically in this regime?
Sorry. Yeah. So again. Sorry for confusing. The only reason I use Q equal to 0 orders, it's easier to explain. Each order, each of the two orders, one has 8 gallstones, one has 6 gallstones. I can start with Q equal to 0 order and then move the system without changing energy by incorporating finite Q orders. So each order generically, is written in terms of, say, two order. It has 8 gallstones. So I can write it in terms of 7 variables.
No. But I'm talking about things like, finite momentum order. Not momenta that bridge the K points, but structure, within the Fermi surface.
This is what you are saying. This is something that we did not do. Erisberg did. And I don't know to what extent this is crucial for us. Yes, it's true. We did not include, we assume that you have small pockets and interaction doesn't care whether it's at 0.
You know very well that fermiology can give you all sorts of structure.
It can. But at the same time, I'll put it this way. Let me try to defend them. You look at the data, particularly for BBG. You see 3 phases, in fact. You don't see 20 phases. Then if you see 3 phases, you may think that maybe if you take minimalistic model.
It's a different question, I guess. It's a perfectly legitimate phenomenology point of view. We turn it around and ask, okay, suppose we don't have the experiment or people are going to do new experiments. Do we have a hope to see more complex, pneumatic, et cetera?
Yeah, and I mentioned at one point, let's not go into it. At one point, experiment tells you that out of 3 small pockets, which I expect to have, there is only 1 there.
So maybe it's a related question that they have. So Levitov has the story that once you have Valley polarization and spin polarization, because the Valley polarization gives you Berry curvature, orbital magnetization that will induce scalar spin chirality and skyrmions. So is that possibility a possibility? I mean, is it possible to get that type of ordering within this treatment?
I think it is, but not with the simple story that I told you. Because I think it requires you to go beyond what I did, my understanding.
Any other question? If not, let's thank Andrey again. Okay, so this is the end of the conference. So first of all, on behalf of the organizers, Lucille, Oleg, Natasha, we would like to thank you all, especially the speakers and those who are coming from far away, for making this possible. So thanks a lot. And 2 quick announcements. So we are going to have a joint barbecue today at 6:30 at the Munger residence. So bring something to eat and to drink. And the other quick announcement is next year we will have a similar workshop in Aspen during the month of July. So the title is Collective Excitations in Quantum Matter by Transport and Spectroscopy, or something like that. So please pay attention and come to Aspen if you can. So thank you all again.